Hey class, I'd like to talk to you about how we can use our slug injection data to estimate discharge in the stream. And this is something that's commonly called dilution gauging. We're using the dilution of our solute tracer to be able to predict what the discharge is in a stream. So before we do this with solute tracer data, let's do a simple example. Let's think about making lemonade from a powdered mix. So if I give you 2 tablespoons of lemonade, and I let you taste the final product, could you estimate how much volume I mixed it in? And if you're not sure about that, let's walk through this as an example. So our goal being the volume of water that I mixed those 2 tablespoons of lemonade powder with. So first consider a case where I take those 2 tablespoons, I mix it with some amount of water, and what I pour for you is an incredibly strong pitcher of lemonade, beautifully illustrated as a picture in the bottom of the screen here. Right? If that lemonade is so strong that it makes your mouth pucker, you would think to yourself, boy, did he use too much water or too little? I used too little, right? I made a very strong mixture. There's a lot of mass dissolved in a very small volume of water. On the other hand, I could have taken those 2 tablespoons and mixed it with an incredibly large volume of water. And in that case, I would have made a very weak pitcher of lemonade. Would have sort of tasted like water with a faint hint of lemon to it. And so, while this is somewhat of a silly example, we know that the volume I used in case 1 must be less than the volume I used in case 2. So we can infer that volume. Maybe put another way, if you know the mass that went in, and you know the resultant concentration, was it strong or weak lemonade, you can estimate something about the volume of water that must have been used in that problem. Now we're going to do that exact same procedure, but with our solute tracer. Let's take a look. So we know how much mass we put in. What we don't know is the volume. But we do know mass and volume are related by concentration. So you could think of concentration as this sort of pivot. Right? Concentration is how you move between a known mass and the volume that it's dissolved in. Now, rather than just focusing on this as one point in time, we can make it a rate. So I can divide both sides of that equation by time, and on the left-hand side I get a mass rate, mass per time, and on the right-hand side I get concentration multiplied by volume divided by time. Now, we can take that volume per time, that's a volumetric flow rate, that's a Q. So we could rewrite it as mass per time equals concentration times discharge. So each of those terms is a mass rate. Okay, let's reorganize it a little bit. Just move that T to the right-hand side. How much mass is there? Well, concentration multiplied by discharge multiplied by time. Now for our breakthrough curve, that doesn't quite work because the concentration is changing constantly. Well, we could envision taking one sliver of that concentration that occurred over a unit of time dt in length, and we could say, well, the amount of mass in that little incremental width, dm, that would be represented by using this equation just for that thin slice. Now those of you who've taken calculus might already see where this is going. Let's take our breakthrough curve, let's chop it into a whole bunch of infinitely thin slices, and then let's integrate underneath it. And what that will let us do is deal with the fact that concentration is continuously varying through the system. So put those little d's to represent infinitesimally small distances or amounts. And then we'll go ahead and we'll integrate both sides. And what we come up with is this equation on the bottom of our screen here. The total mass is equal to the integration of the concentration time series multiplied by discharge through time. We're going to pull the discharge out front. So we're going to assume that that discharge is steady state. In other words, the discharge is not changing during our tracer injection. And we're left with the equation mass is equal to discharge times the time integral of our concentration time series. So mass we know, we put that in. We mix that in a bucket and put it into the river. Concentration we measured. Time we know, because we were also recording when we made those concentration measurements. So we ought to be able to get to a discharge. Let me show you exactly how that works. Getting to Q. So rearranging what we had on the previous slide, we get this. Discharge could be estimated as the mass divided by the time rate of concentration. Now in order to pull this off, you've got to meet that requirement of steady flow that I discussed on the previous slide. You have to know the mass that you put in and be able to accurately measure the concentration time series. In other words, that C sub T needs to be accurate. You need to have measured that concentration at a location that's representative. In other words, you need to be at a place that's well mixed in the stream channel so that you're not getting just the center of the channel where the concentration might still be spreading. You want a representative concentration in the cross section. And importantly, this formulation assumes that 100% of the mass is contributing to the concentration. In our example that we did early on, this assumes that I didn't take those 2 tablespoons of lemonade powder and throw one over my shoulder, but all of that lemonade powder made it into the pitcher. Similarly, all of your tracer mass is expected to contribute to concentration. Now this sets up a bit of a dilemma for how you operate in the field. Because you want a representative concentration, you need to be downstream far enough to ensure that it's well mixed. But because you want to make sure that all of the mass contributes, you want to be as close to the injection as possible. So you're minimizing mass loss into transient storage or hyperetic flow paths or someplace that may not come back within your window of detection. So for dilution gauging, our goal is to be downstream far enough to have complete mixing, but as close to the injection as we possibly can. So this is something that you might end up having to try a few times in the field to get a sense of how your system is working. Okay, with this information in hand, you should be able to take an injection of a known mass with an observed concentration time series and use that as a basis to estimate volumetric discharge in a river, which you will do in your next learning activity. Thanks, everybody.